Practice 4. Respiratory volumes. During this practice, the team acquired general knowledge related to respiratory volumes, pulmonary capacities, and their relationship between them. We combined the use of a pneumotachometer with the development of a BI using LabVIEW to calculate the pulmonary capacity of one test subject. The main objectives of the practice focus on the design and implementation of a system capable of recording respiratory flow and calculating lung capacities from this record, and to compare the obtained values with those expected of such subject. As a short introduction, we can mention that lung volumes, also known as respiratory volumes, refer to the volume of gas in the lungs at a given time during the respiratory cycle. Lung capacities are derived from a summation of different lung volumes. The average total lung capacity of an adult human male is about 6 liters of air. These volumes tend to vary, depending on the depth of respiration, ethnicity, gender, age, body composition, and in certain respiratory diseases. Here, we can see a graph of lung volumes and capacities, where we can see that lung volumes include tidal volume, which is the amount of air that can be inhaled or exhaled during one respiratory cycle. Inspiratory reserve volume, the amount of air that can be forcibly inhaled after a normal tidal volume. Expiratory reserve volume, volume of air that can be exhaled forcibly after exhalation of normal tidal volume. Residual volume, volume of air remaining in the lungs after maximal exhalation. On the other hand, lung capacities include inspiratory capacity, which is the maximum volume of air that can be inhaled following a resting state. Expiratory capacity, maximum volume of air that can be exhaled following a resting state, is the result of the sum of tidal volume plus expiratory reserve volume. Total lung capacity, maximum volume of air the lungs can accommodate after maximum inspiration. Vital capacity, total amount of air exhaled after maximal inhalation. Functional residual capacity, amount of air remaining in the lungs at the end of a normal exhalation. This table contains normal values for lung volumes, such as tidal volume, with a normal value of around 500 milliliters. The inspiratory reserve volume normal value is between 1,500 to 3,300 milliliters. The normal expiratory reserve volume is between 700 to 1,000 milliliters, and the normal residual volume is between 1,100 to 1,200 milliliters. On the other hand, the inspiratory and expiratory capacities are calculated by adding the tidal volume plus the inspiratory and expiratory reserve volumes, respectively. The functional residual volume is the sum of the expiratory reserve volume plus the residual volume. The vital capacity is the inspiratory reserve volume plus tidal volume plus expiratory reserve volume. And finally, the total capacity is the sum of all the results obtained through the previous capacity equations. Next, we can see a Lilly pneumotachometer. In general, the pneumotachometer converts the flow of gases through it into a proportional signal of pressure difference on either side of a central mesh, whose design ensures a signal linearity over a range of flow rates with a minimum dead space. Here, the circuit developed to record the respiratory flow is presented, which consists of a vernier brand spirometer with a piece of paper inserted in the mouthpiece for hygiene reasons, connected to a protoboard using an analog protoboard adapter or BTA connector, and this in turn connects to a NI USB 6009 data acquisition card from National Instruments. Jumper wires are used to connect the output of the BTA to the analog input port 0 of the data acquisition card, along with the ground connection to ensure a common reference. It is important to provide the necessary power to the BTA, which involves connecting a jumper wire to the 5-volt supply available on the National Instruments card.
Continuing with the circuit created with the LabVIEW software, a variety of blocks were used including the DAQ assist, which will serve to provide information to the program from the physical information obtained. Then, a sensitivity value will be placed by multiplying the signal by 7.8. This value was obtained in the datasheet. After this multiplication, a sum with a value of 19.7 will take place, which will act as an offset to center the obtained signal. From here, two paths will emerge. One without any other type of operation that will lead to the flow, and another that will integrate the flow signal to get the volume. Finally, connected to the resulting signal of the volume will go a block called read to measurement file that has as a function to convert the signals obtained in a file of format txt. This is done to create a complete chart capable of presenting the complete signal, allowing the team in question to analyze it. In order to get the right signal, it is important not to do any of these things when taking samples. First, it is important that the user does not inflate the cheeks, as this will cause changes and alterations in the results. Another important thing is not to tilt the device or keep the head well positioned above the device at the time of the sample. The correct procedure to follow to get the most accurate results possible is first keep the device in an upright position. You should also cover the flow of the nose as shown in the video, and finally it is important not to inflate the cheeks while breathing. The results obtained after data collection and analysis are shown below. First, the signal that was obtained from the circuit using an oscilloscope is shown. The following two graphs show two different samples obtained from respiratory flow. Following that slide, two different graphs showing the respiratory volume obtained by the circuit are found. Next video shows samples of forced inhalation and exhalation. This technique is done to measure the inspiration and expiration capacities. Then, the complete graphs obtained by these techniques are shown. In this, you can observe the drastic falls and rises in the signal. These are the expirations and inspirations respectively. Using these graphs, it is possible to find the tidal volume and the inspiratory and expiratory reserve volumes, as shown in the image. Using the technique shown on the last slide, the following tidal volume was reached. Using the cursors led to the conclusion that the operation to obtain this value would be 1.3 minus 0.7, resulting in 0.6. So the tidal volume obtained is 600 milliliters. Take out the inspiratory reserve volume. Similarly, the cursors were used. After doing so, this equation was obtained, 3.26 minus 0.64, reaching an inspiratory reserve volume of 2600 milliliters. For the expiratory reserve volume, the same procedure was used. This led to the following equation, 1.46 minus 0.46, obtaining an expiratory reserve volume of 1 liter. It is important to note that with the values obtained throughout this experiment, it is not possible to calculate the residual volume, so it was necessary to make an approximation. To obtain the total capacity of the lungs of the subject, the following values must be added: tidal and residual volumes, and the inspiratory and expiratory reserve volumes. Adding all this together, the total lung capacity was 5.3 liters. Finally, to conclude the practice, the following conclusions were reached. First, the results obtained fall within the expected range. The graphs are clear and allow the correct measurement of the values sought. The team achieved a deeper understanding of lung capacities and volumes, and the objectives set at the beginning of the practice were fulfilled. Thank you.